Salam and welcome, everyone. So today we're going to be working on the question on the screen that says a sample of CO2 gas of mass 2.45 gram at 27 degrees Celsius is allowed to expand reversibly and adiabatically from 500 centimeter cube to 3.00 dm cube. What is the work done by the gas? The value for CV, M for this question is 28.14 joule per mole Kelvin. So the first thing you have to note is for the solution is for you to write out all the parameters that we're given. We're given the mass to be 2.45 gram. We're given the initial temperature for this particular question to be T initial to be 27 degrees Celsius. And we can just simply convert it to Kelvin because that's how we want our questions in thermodynamics. We always want it in Kelvin. So we can just say 27 plus 273.15. So that's just going to be T initial is going to be 300 Kelvin. Sorry, 300.15 Kelvins. We have is allowed to expand reversibly. Okay, so we have an irreversible expansion as well as adiabatically from 500 centimeter cube to 3.00 dm cube. So this is an adiabatic reversible expansion process. So we have to keep that in mind. So we're going to put our information down. We have the V initial to be 500 centimeter cube, and we have our V final to be, so let me rewrite the V final. We have our V final to be 3.00 dm cubed. And we're asked to find the work done by the gas. So we're actually looking for W. Part of the question is to tell us the value of the heat at constant, the molar heat capacity at constant volume. And we're told that we're going to use 28.14 joule per mole Kelvin. Now, I want to mention this. This was not in the initial question. I'm the one giving you the value to use. You could end up going online or having a question and you're going to be giving a totally different value, but this was not in the question. This is the best value I thought we could use for this particular question. So you can go online and find the molar heat capacity for carbon dioxide, and it's going to be slightly different, but the 28 is still there, but the decimals after the 28 might be a little different. The next thing we have to do is that we're told to find the work done. In order for us to find the work done, we have to note that we have to, part of the formula for work done is for us to know the final temperature, because the work done formula is W equals the number of moles times the molar heat capacity at constant volume times change in temperature. There's no way for us to be able to find the work done if we don't have the value for change in temperature. In order for us to find change in temperature, we have to have the final temperature, and which we're not given. So the first thing is now write out the formula for final temperature. So let me just erase this right here. Formula for final temperature in a reversible adiabatic expansion process is just T initial times V initial divided by V final. All of this information raised to the power of 1 over C, where C is equal to the molar heat capacity at constant volume divided by the gas constant R. So that's basically what we're doing. I don't want anyone to be confused. I know I just said a whole bunch of stuff, but it's doable, right? It's absolutely doable. So let's find what our value for C is. We have the initial temperature given to us. We have the final volume given to us. We have the initial volume given to us. But the only issue is that our initial volume is in centimeter cube. We have to make sure that both initial volume and final volume are in the same units. So let me quickly solve what C is, and then we're going to convert 500 centimeter cube to dm cube. That has to happen in order for us to properly substitute. So C equals CV, M. So that CV, M is just what we're given, 28.14 joule per mole Kelvin divided by R. R, of course, gas constant. So that's 8.3145 joule per mole Kelvin. So you cancel out joule and mole Kelvin, joule and mole Kelvin. So that C is actually going to now equal, C is equal 28.14 divided by 8.3145 is just simply 3.3844. So that's going to be the value for C that we're going to use in this question. So yeah, that's basically it. So the next thing we have to do is for us to convert the initial volume. The initial volume, let's not forget, is V initial is, we're told it's 500 centimeter cube, and we're trying to go to decimeter cube. So in order for us to do this, we have to remember that one um one um one decimeter cubed is the same thing as 1000 centimeter cubed. Hence, 500 centimeter cubed is going to give you what? Let's use the value. Let's use the unknown value x. So if we do this, we can cross multiply and we end up with 500 centimeter cube decimeter cubed is equal to 1000 centimeter cubed x. So we're trying to find x, right? Let's cancel out centimeter cube here because we're actually trying to solve for decimeter cube, and we have two units on both sides of the of the equal sign, and we can just simply cancel that out. So x is now going to equal 500, okay, decimeter cube divided by 1000, and that's equivalent to x equals to 0.500 decimeter cube. So that's basically the answer to that. So yeah, let's go up and write the v initial, the proper v initial that we're going to be using in this question. It's going to be 0.500 decimeter cubed. So of course, let me clean all of this part. We've gotten the value we need to get for this. We actually even have the value for C. So I can just write C up top here. So C is actually 3.3844. So I'll write that 3.3844. So I'm just going to basically substitute on this part. So T final is going to equal T initial, which is 300.15 Kelvin. And then V initial, substituting it, we have 0.500 decimeter cubed. Divided by, of course, V final, which is 3.00 decimeter cubed. All of that information is raised to power 1 over C. So 1 divided by C, that's 3.3844. So that's basically it. Let me rewrite this. What's the power of 1 over 3.3844? So, of course, cancel decimeter cube here, cancel decimeter cube. So C final is equal to 300.15 kelvins times this information here. This information here, you put it in your calculator, meaning 0.500 divided by 3 raised to the power of 1 over 3.3844. You have to learn to input complex information into your calculator, and input that in my calculator, I ended up getting 0.58892. So that's basically what I got. So that's the information here. Now I can now use this information here and multiply by the initial temperature here to find the final temperature. So T final is going to end up being 300.15 Kelvin times this information, which is 0.58892, and you end up getting 176.764 Kelvin. So this is what we're going to be using as the final temperature. Now, let's not forget that our work is not complete. Our work requires us to find the work done. So let's not forget that the formula for work done is number of moles times the molar heat capacity at constant volume times the change in temperature. We have the molar heat capacity at constant volume given to us, and we can find the change in temperature. But the issue is we don't have the number of moles. Well, we know that looking back at our question, we have a CO2 gas and we're told the mass. We have the mass, we can calculate the molar mass, and we can find, of course, the number of moles. So the mass of what we're given is 2.45. Okay, we have the molar mass for CO2, which I don't need to solve because we're above that process of writing that out. You guys can just solve it on your own or Google it. That'll be 44.009 gram per mole. Okay, so the mass is gram. So number of mole will be mass divided by molar mass. So that'll be 2.45 grams divided by 44.009 gram per mole. So cancel out grams, cancel out grams. The number of moles here would be 0.055670 mole. So that's basically how it's done. So the work done adiabatically would now be us substituting this information. So I'm going to end up with 0.055670 mole, okay, times the molar heat capacity and constant volume. Going back our question up top, we see that is 28.15 joule per mole Kelvin. So that would be, let me actually erase this information. We've gotten the number of moles that we need. So times the molar heat capacity at constant volume, we know that to be 28.14 joule per mole Kelvin times change in temperature. So T final divided by T initial. So we have our T final to be 176.764 kelvins minus the T initial. Going back to our question, we see that is 300.15 kelvins. So that would be minus, oh, what's going on? Minus 300.15 kelvins. So of course, W adiabatic would just simply be 0.05567 mole times 28.104 joule per mole Kelvin times negative 123.386 kelvins. So of course you cancel out the kelvins, cancel out the kelvins, cancel out the mole, cancel out the mole. So that would be W adiabatic is going to be 0.05567 times 28.14 times negative 123.386. So all of that information would be negative 193.291 joules. And of course, we have to go back to the fundamentals of what we know chemistry to be. We have to look for the lowest number of significant figures, and we're going to have to put our answer in that. We see 2.45, 500 centimeter cube, and 3.00 decimeter cube. All of this information is in 3 sig figs, so that means our answer is going to be in 3 sig figs. So W, work done adiabatically, or adiabatic work done is negative 193 joules. So this is the answer to this particular question. If you have any questions, please put in the comment section. If you have any concerns or suggestions, also put in the comment section. If you're a student who is trying to succeed in all your STEM related courses, in whether you're in middle school, high school, or college, make sure you email me at shohabitutoring@gmail.com in order for you to just book a free session and just learn about the services that I render. I help students who are trying to be the best version of themselves in their academic career to succeed in that particular goal, as well as in other academically inclined goals that they may have. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.